as you can see, the title of the second part of my set is telling you we are trying to investigate into more details to a more simplified transmission called lossless transmission. So at this point, you have to think, what does lossless mean? Lossless means it's better, easier, right? And the professor is kind to you. Or the professor is just lazy because it's a simplified version. But when I talk about a lossless transmission line, what elements am I trying to omit? Lossless, if you remember. If I have loss, which lumped elements are introducing loss? Resistors, right? So lossless transmission line means I have a very simplified model for the transmission line. I only have inductor and capacitor. Now, if you still remember, inductors and capacitors are energy storing elements. They store energies. They convert energies to electrical form or magnetic form, but they don't waste energies. Alright, so by definition, if I'm now focusing on a lossless transmission line, my circuit model would only have inductors and capacitors, which makes sense. Now, we understand the picture. Do we need to re-derive everything? Lossless transmission line. Do we have to derive, start from KVL, KCL all the way here? Spend another 60 minutes? Of course not. All we have to do is, as I said, for a transmission line, everything is contained in the knowledge of gamma and characteristic impedance, right? So, gamma in the lossless case, there's no loss, there's no resistance, no conductance. Simplified version. Characteristic impedance. Simplified. Right? I'm a very nice guy. I'm going to show you the results. Without loss. Characteristic impedance is the square root of L prime divided by C prime. Right? Here. Let me write it for you. Lossless. Z0 is now L prime divided by C prime. Gamma. Gamma, by definition, is no alpha. Right? There's no alpha. Alpha means loss. Now we're talking about a lossless transmission line. This has to be 0. Gamma is now omega L prime C prime. This is beta. Okay, purely. If you imagine J, and that is equal to J 2 prime divided by 1. Okay. So if we have a lossless transmission line, things become simplified. Okay, so the wave travel, there's no loss. So different geometries and different materials used to construct your transmission line will in turn change its propagation constant and its characteristic impedance. Okay? So the way I like to teach transmission line as the first topic for this course is throughout the entire semester, you will be able to derive the corresponding C prime and L prime, R prime and G prime. Okay? So we start with a target and we use the entire semester to understand it, to approach it. Okay? Now, let me try to dim the light, okay? Because I tend to use, probably starting from now on, I want to use the PowerPoint because the math derivations are very messy. Okay, so this is a recap of what we learned from the last 100 minutes. We only have 15 minutes left. So voltage phasor with a hat as a function of space is having a positive propagating amplitude plus its propagation form plus a negative reflected wave. Right? And the current, by now, we know that the current amplitude is nothing more than the voltage amplitude divided by the characteristic impedance. Again, be careful. For the reflected current amplitude, it takes on a negative sign because you're sending power back to the generator. It needs to have a negative sign. Okay. So now the question is, I have two equations. I have two unknowns. The number of unknowns is equal to the number of equations, which is okay. So I started with 4 unknowns. By introducing Z0, I have 2 remaining voltage amplitudes. So the number of unknowns is now 2. So I should be able to acquire complete information now. So the process flow now really depends on your understanding. So I'm showing you a real system. I have tie power, right? Tie power. I have a generator. The generator itself might have some internal impedance. And the power is delivered to us through the transmission line. And we, the users, are connecting, plugging our components into the outlet. And that component has its own load impedance, ZL, capital L. So try to link this picture to these two equations. Question number 1. Where do you want to define Z as 0? What kind of question is that? Doesn't matter, right? The equation is equation. Z, V as a function of Z. Z can be 0 here or can be 0 here. I'm trying to ask you, in the past, we usually define Z equals to 0 at the input, right? For convenience, the input is 0, so this is maybe 10 kilometers, right? I know my distance. If you want to use Z equals to 0 at the input, where your generator is, which is also fine. But the trouble you run into is, if you want to know the voltage values or the current values at the load. V of L, L means the length of the transmission line. These exponential terms do not disappear. Then your mathematical derivation will be very, very messy. Okay? And the second reason is, why do we care about the voltage and current here at the load? Why? Let me
We know the load.
The load is inserted into the wall outlet by us. That is a well-known parameter. So if you know the load impedance, ZL is, by definition, is V at the load divided by I at the load. But that is known, right? Do you follow my philosophy? So on a transmission line, if I want to properly use a transmission line, I do care about how voltage and currents are changing along the line. But more importantly, I really care about the message or the information of the power delivered into the load, right? That's the most important message I need. So I really care about the voltage at the load and the current at the load. But the voltage at the load divided by the current at the load is determined by my load impedance, which is defined by myself. So really, these equations should be using Z equals to 0 at the load. Think about it. What's the benefit? If I define Z equals to 0 at my load, V of the load, meaning Z equals to 0, exponential terms are all ignored, right? Exponential J0 is 1, right? So all these 4 unknowing components are replaced by 1 at the load. So be careful and look at this definition. Okay? Usually, although we want to define Z equals to 0 at the end, at the input, but here in this particular case, from now on, we are going to define Z equals to 0 at the load. And we are trying to solve everything at the load and walking back or tracking the answers back to the input. So for this reason, I'm trying to define a new distance variable. So Z is 0 at the load and positive going in the direction from left to the right. But at the same time, can I also define a new distance variable as D? D is 0 at the load as well, but it is positive going back to the generator. Okay? So this is saying I am defining this D equals negative Z, which is fine. So let me repeat myself again. For simplicity, for convenience, I want to analyze the system with the load with a value of Z equals to 0 and d equals to 0. Z is pointing from the left to the right. D is pointing from the right to the left. The only difference is the direction. Okay? So D equals to negative Z. Okay, so now we are capable to start an analysis now. How much time do we have? 6 minutes. Maybe enough, maybe not. So what I know is VL, the voltage at the load, is V of 0, right? Z equals to 0. So this is directly V0 plus V0 minus, right? IL is I at 0. This is Z0, V0 plus minus. Right? Now you can see why I want to define Z equals 0 at the load, because mathematically very simplified. Okay, so Z load is VL divided by IL, which is, well, you have to perform the division. V0 plus V0 minus V0 plus minus V0 negative times S. Okay. Remember, what are we trying to do? We are trying to solve for V0 plus and V0 minus. Does it help to further reduce the number of unknowns to just one? Look at the equation. If you look at this equation, at the load, we have this mathematical equation, but does it also tell us once we connect the transmission line to a known load, we already know the ratio between the reflected voltage and my input voltage. Okay, so let's do it. So I'm trying to multiply this thing to the left. So ZL. So this is the equation I want to use. I want to use this fact. Having any reflection is because of the load. So at the load, with a given load, I determine the amount of reflected wave. Okay? So using this, I can gather around V0 plus is ZL minus So this is what I have. Using the knowledge and defining z equals to 0 at the load, I somehow realized my reflected voltage amplitude is directly determined by the difference of my load to the characteristic impedance of the transmission line divided by their sum. So this is further telling me, hey, everything is even more simplified. Having the load connected to the end of the transmission line, I can somehow relate V0 minus to V0 plus with a known reflection coefficient. This gamma V is called a voltage reflection coefficient. Then, the entire system can be solved just by knowing what the forward voltage amplitude is. And everything's being solved. Okay? So think about it. We started today from KVL, KCL, running down a lot of equations. Eventually we have 4 unknowns. But then we found out the transmission line has this beautiful characteristic. Voltage divided by current for certain propagation direction will be a constant. Maybe positive, maybe negative. Then we can reduce the number of unknowns to 2. And then at the load, we can further relate the backward voltage amplitude to the forward voltage amplitude by a reflection coefficient. Then we only have to solve for the positive voltage amplitude. So we spent 100 minutes to arrive at this point. So on Wednesday, please do review the materials. Please. On Wednesday, we will encounter even more mathematical derivations. But again, like I said, I want to emphasize on physical meanings. Okay? So on Wednesday, I tend to use a PowerPoint. Maybe I won't be writing so many equations on the board. You can look at the equations on the PowerPoint, but try to understand what the derivations mean in physics. Right? So on Wednesday, we will understand, we will be able to solve for the transmission line completely. And maybe if time allows, we are going to talk about the particular loads. What do particular loads are going to affect the resulting voltage and current behaviors along the transmission? All right, so let's start.